let's move on and talk about something called countability. This kind of connects to what you said yesterday, something about counting things, which maybe is more kind of clever than you thought it was. But we say that a set is countable if either one of the following two things happens. So if it's finite, so any finite set we say is countable. I guess for obvious reasons, because if you have a finite set, you can count it. It might take you a long time, but you can count it. Or if the size of A, if A has the same cardinality as the naturals. Now, in some sense, you can't really count the naturals because you'll never stop. But if you're sort of allowed to count forever, you can count them, right? You can list them in order and go 1, 2, 3, 4, etc. So if a set has the same size as the naturals or it's finite, we say it's countable. And in the second case, we say it's, sometimes you might see the words countably infinite.
Is the reason why you say that the naturals are countable because you have a starting point to start counting, whereas like the negative and positive integers, you don't really have a starting point, so you can't that one?
That's a good question. Well, here's the thing, you can have a starting point. So let's let me do that as an example. So the integers do have the same size as the naturals. The integers are countable. Even though it doesn't, yeah, you're right, it doesn't seem like there's a good starting point, because if I start at 0 and I go off in that direction to the positive direction, I'm not going to get the negatives, right? But what if I just do it a bit more carefully? I start at 0, I go to 1, I go to -1, I go to 2, I go to -2, I go to 3, I go to -3, and I bounce back and forth. So I'm going to define, I mean, maybe I won't do this one completely carefully, kind of according to the following picture. Which perhaps is not the most rigorous way to define a function. But what I'm going to do is I define f of 1. So f of 1 is 0. F of 2 is 1. F of 3 is -1. F of 4 is 2. F of 5 is -2. And you can kind of see what I'm doing. I'm kind of bouncing back and forth. Okay. I think maybe one can technically define this with some kind of a formula, but maybe we shouldn't do that. But yeah?
What about the case of like the rationals of the real numbers? Why can't we count those?
That's a good question. So the answer is going to be that the rationals are countable. The reals aren't. So so that's, I mean, if that somehow blows your mind, we're going to see a proof of that on Friday. So I know it's the last Friday of the whole term, but yeah, that might be it's going to be a cool lecture. Yeah.
Is that what Fn, is that equal to the F?
Oh, sorry. Oh. This is a colon. So this is a function. I'm defining a function from n to z. And sort of I mean, I could probably write a proper definition of this by saying, but yeah, maybe I don't really want to. But you can write a formula for this, right? Which is kind of saying the odd numbers. Essentially, I'm taking the odd numbers and I'm mapping them to the negative numbers, right? So 3, 5. Okay, 1 maps to 0. 3, 5, 7, etc. are going to cover all the negatives, and all the even numbers are going to cover the positives in some sense. So if you do it that way, it is countable. You can show it's countable. It should be clear this is going to be a bijection, right? I'm not going to map two things to the same point because I keep bouncing further away from 0 every time, and I'm going to cover everything exactly once. Okay. Let me tell you a good way to show that something's countable. So essentially what you could think of here, you can think of the values f1, f2, f3, f4, etc. as being a sequence, right? So the point here is that is a sequence that includes every element of the integers. And in fact, it includes every element of the integers exactly once. It turns out this thing about including it exactly once is not actually really necessary, though. So I'm not going to give a proof of this, but there's a proof in the notes. It's just kind of it's not hard to prove, it's just kind of annoying. But essentially, understanding the statement is the key thing. The proof isn't particularly enlightening. So the theorem says a set A is countable if and only if there exists a sequence. So let's call it, maybe let's call the sequence x1, x2, x3, dot, 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 which includes every element of A. So you should think of this as being sort of just an extension of this construction here, where the point of this is we were essentially, yes, I was defining a function, but essentially the point is I'm kind of defining a sequence of numbers, of integers, which cover every integer at least once, right? And it turns out that that's exactly what it means to be countable. So a set is countable if you can make a sequence that covers everything in A. Because essentially, that gives you a method for counting the elements of A. What you would do is you just go along your sequence, and whenever you see a new element of A that you haven't seen before, you count it. Like you said, your counter goes up by 1. So go along your sequence. Every time you see an element of A you haven't seen before, increase the counter by 1. And this sort of counts all the elements of A because every element of A appears in the sequence. So that's kind of another meaning of the word countable. This turns out to be kind of a useful definition. It's actually kind of more useful than dealing with bijections because, for example, it's going to make it really easy for us to show that the rationals are countable because we don't care about going back to the same rational number more than once. Okay. Let me give you another example of how this works. So it's kind of similar to this example. So I want to show that the naturals cross the naturals is countable. So to do this, I want to find, so my goal is to find a sequence which uses every element of n cross n. Do we remember what n cross n even is? I mean, a good way to kind of draw this, right, is sort of in a kind of a grid or an array. So n cross n contains the point 1, 1, right? So n cross n is essentially all the pairs of positive integers. It also has the point 2, 1, 3, 1, 4, 1, etc. So we just, you have infinitely many points. So I'm just kind of increasing the x coordinate here by 1. You've also got the point 1, 2, 1, 3, 1, 4 in this direction. And then you've got you can kind of fill up the grid here. So that would be 2, 2. That would be like 4, 4. That would be like 2, 4, etc. Okay. So essentially, I want to take some sort of a sequence that covers everything in this infinite grid. So this grid goes out infinitely in both directions here, right? So let me tell you something you shouldn't do. I mean, a sort of bad idea is to start by just taking, I'll start at 1, 1, and I'll go to 2, 1. And then I'll go to 3, 1, and 4, 1, and just go along this line. But that's sort of the same problem we had with the integers, right? If you start at 0 with the integers, and you try to cover all the positive ones first, you'll just go off to infinity, and you'll never get around to doing the negative ones. So if I just sort of try to cover all this bottom row first, it's never going to end. So I'm never going to get to start at this row and go across. So the sort of clever thing to do is to sort of work your way around the grid in a sort of pattern like this. So this is something called diagonal sweeping. So we'll start here. So this is going to be my first element of the sequence, x1. So x1 is 1, 1. I'm going to go here. I'm going to go across. I'll go up here. I'll go down, down, up. Oh, sorry, not up. Over to the next diagonal, across, 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 up. And so on. So essentially, I'm kind of wiggling around. Yeah, whenever I get to the sort of wall here, I go up. And whenever I get to this kind of bottom thing, I go to the right. And then I go diagonally, I go up. I go diagonally, I go right. Okay. So this would be my x1 is here, x2 is here, x3, x4, x5, and so on. Okay. Is it clear that this is going to cover everything? Right? Because on every diagonal, I go finite, sort of the distance to the other kind of wall here is a finite distance, and then I move to the next diagonal, and I go down. Essentially, so the first point. So first, we're going to cover the point 1, 1, so essentially we're covering points based on the coordinate sum. So here the coordinate sum to 2, and then we cover the points where the coordinates sum to 3, so 2 plus 1 and 1 plus 2. And then where they sum to 4, 1 plus 3, 2 plus 2, 3 plus 1. And then where they sum to 5, and then 6, and then 7, etc. So basically, you start by taking the smallest coordinate sum, cover all of them, and move up and up and up. Okay. Yep. It still works, yeah. That's a good point. So here I'm actually, that's kind of the useful thing about this theorem, is I'm saying actually it doesn't matter if this has repeated elements. So you just have to, you can have repeated elements. Yeah, that's kind of important point here. So this one doesn't have any repeated elements, but you can if you want. Okay. Let me just show you a quick modification of this, which gives you the rationals. So, and this one is going to have repeated elements. So Q is countable. So to show this, we essentially do the same sort of thing, except we sort of mix these two strategies. So I had this one for n cross n, and there was a slightly different thing with z cross z, where I jumped back from positive to negative, so that I got all the negative numbers. So Q has negative numbers, so we need to kind of do that. But at the same time, we need to sort of do something like this. So here's the diagonal sweeping strategy here. So I start with the number 0 over 1. So my bottom row, I'm going to list all the rational numbers that have a denominator of 1. But I have to be careful because I need to get the negative numbers too. So I need to jump back and forth from positive to negative. Sorry, so that should be 2 over 1. Okay, on my second row, I'm going to write the rational numbers with a denominator of 2. And note that, of course, these are the same number, right? 0 over 1 and 0 over 2 are the same. But just to make things just to make the picture clear, I'm going to write them, essentially I'm writing this number twice, right? But that's okay. And now I have negative 1 over 2, positive 1 over 2, negative 2 over 2, which is the same as negative 1, of course, but it's okay to repeat it. 2 over 2. And then I take the fractions with a 3 on the bottom. Is it clear what this picture is doing? And is it clear that this picture is going to contain all the rational numbers? It's going to contain them many, many times, but it doesn't really matter. Okay, and then I just do this diagonal sweeping. I start with my first element here. I go here. I've kind of made this picture not the greatest, but it's the same kind of trick as before. But this is an example where you will have repeated elements, because the first element of the sequence is 0, but also the third element is also 0. But because of this theorem, it allows me that is written on this board back here. You're allowed to have repeated elements. Yep.
Would it like this be a valid proof on that?
Yeah, this would be a proof by itself. Yeah. So you could sort of maybe throwing in a sentence like, kind of we apply diagonal sweeping or something. And then sort of let x1, x2 be the sequence defined by the following picture. If you look in the notes, like this is essentially what they do in these examples. If it's good enough for the notes, it's good enough for you as well. So, yeah. Yep.
What would you consider the one where we kind of like jump forwards and back, because that's not diagonal sweeping, right?
That's a good point. Yeah, so maybe it kind of is, yeah, flip-flop technique. I guess I don't have a technical term for that, but maybe you could just start with this, kind of let x1 blah, blah, blah be kind of defined by the, for that one you could probably just come up with a formula for the next element of the sequence or something, but yeah, you don't necessarily have to. Yep. Yeah, so you can literally define, say, you write like xn equals, and kind of come up with a formula for it. In this case, it's going to be kind of an ugly formula, but you could, if you kind of think of what each element of the sequence is, you could probably do it, but I wouldn't recommend it actually. This is probably a better way to go about it. So let me just sort of review a few different ways you can show that a set is countable. So these aren't the only ways to show that a set is countable, but these are the main ways that we can do it in this class, basically. So ways to show that a set A is countable. So, okay, well, here's almost a silly one, but it's important to remember this. One way you could do is just show it's finite, So show that A is finite. If you're just given a finite set, you can just say right away, this thing's countable because it's finite. Another way is to show that A is a subset of a known countable set. So show that A is a subset of a known countable set. So when I say a known countable set, what I mean is, something we've proven is countable in the class, in the course. So for example, actually, the naturals, we never proved it's countable, but that's basically the definition of countable. Um, we showed that the integers are countable, the rationals, n cross n, you know, so yeah, etc. So if A is a subset of a countable set, it's automatically countable. So a third way to show that a set is countable is to use this theorem we stated last time, which says that if there's a sequence of sequence which covers every element of A, then A is countable. So find sequence x1, x2, x3, etc., such that every element of A appears in the sequence. So an example of how to do this is, for example, using this diagonalization trick. So, for example, sorry, not diagonalization, but diagonal sweeping. So that diagonal sweeping was one way of showing that there's some sequence that covers all the elements of some set. Okay, it's not the only way to do it, but it is one way. A fourth method that I want to kind of briefly mention, and maybe actually after this we'll actually prove that this works. So what you want to do is one way to show that A is countable is to show that A is a countable union. So I'll explain what this really means in a second. Of countable sets. Okay, what does, countable sets, I think we understand what that means. It means that the sets are countable. We understand what a union is, but what's a countable union? So let me explain a bit more specifically, or more rigorously. So what I want to prove is that if I take a bunch of sets, A1, A2, A3, ... So this is an infinite sequence of sets. So if they're all countable, then, so these are countable sets, then the union, well, okay, maybe notation-wise, let's write this as A1 union A2 union A3 union, and then I'll write ... to mean we take the union of all of these sets. So it is countable. So this is what I mean by a countable union. You've got a countably infinite number of sets, and all of them are countable, and you take the union of all of them. So this is what I mean by countable union of countable sets. Any questions about this? I'm not sure if the meaning of this is clear, but imagine you take the first set, you union it with the second set. Union means you take all the elements in both sets, right? And then you say, okay, well, in other words, remember the union is like an OR, right? So this is the set of all elements which are in A1 or A2 or A3 or A4, et cetera, et cetera. Okay, so let's prove this. So it turns out that this can be proven just using the same diagonal sweeping trick we used before. So well, okay, this is maybe a little bit. Oh well, no, this is okay. So all I need to do is I need a little bit of notation. So I need a way of writing the elements of, let's say, A1. So I'm going to write the elements of A1 as A11, A12, A13, A14, etc. So all of them sort of have two kind of indices. Maybe I should put a comma between them, where the first index says that we're talking about set A1. The second index is like, this is the first element of A1, second, third, fourth, etc. And note that, so I'm kind of writing this as an infinite list, but of course, there's a little technicality. A1 could be finite, but if A1's finite, just write this list, but just repeat elements over and over if you want to. Because remember, when you write a set, if you repeat elements, they don't count twice. So, just a technicality. You could write A1 as an infinite list, even if it's a finite set. More generally, so for each set AI, we're going to let AI be the set AI1, AI2, AI3, AI4, and so on. So all I'm doing is giving you some notation for talking about the elements of AI. I mean, there's nothing really, I'm not proving anything here. Okay. Any questions about that? So here's the trick. I mean, the trick is the same as all of these countability proofs we've done so far, which is like something like diagonal sweeping. So suppose I write a sort of, I draw a picture where I take the elements of A1 and I write them on the bottom. So that's A11, A12, A13, A14, ... So you have to have some imagination here that I'm actually writing an infinite list of numbers here, but obviously I can't actually do that. But you can kind of see how this continues, right? So now A21, A22, A23, A24, ... By the way, the fact that, the reason I'm actually allowed to list the elements of AI is because all of these AIs are finite, or sorry, not finite, but countable, right? So I'm using the countability to say that I can list out the elements, because that's really what countable means. Okay. So then you kind of imagine I extend this picture infinitely, in all kind of directions. And now I can just do some diagonal sweeping here, right? I start with this element. So by the way, so A is the union of all of these sets, right? So A is the set of all elements in this picture. And I want to show that there's a sequence that contains all, just an infinite sequence that contains all the elements of A. So what I can do is start here. I start my sequence here. I take a step over here. So this is the second element of my sequence. This is the third. This is the fourth. This is the fifth, sixth, seventh, eighth, ninth, 10th, and so on. I go up here, I go down, I go over, I go up. And that proves that A is countable. So essentially, you can say let x1, x2 dot, dot, dot be the sequence defined as in this picture. And this would be good enough, I mean, essentially on a test, as long as the picture you draw makes sense. Like if it really is going to cover all the elements, and it's clear from the picture. And now you can just say, okay, so every element of A is covered. Therefore, A is countable. Okay, so a countable union of countable sets is countable. So that gives you another way of showing a set is countable. Okay. So kind of the most, I think, yeah, the best trick we have right now is diagonal sweeping. So, I mean, actually, probably if you remember how to do this, then, I mean, that's probably going to work for any countability proof that you're going to see. But it's good to know all of these other things as well.